Lab 5 and 6, Part 2. We'll be collecting the data for after the separation. So once we have left all three components to dry for the week and come back to get their masses. So after the separation, we come back to lab and we remove both beakers from the oven to find solids, dried solids, and we also retrieve the watch glass with the filter paper and solid on it. So we're collecting data and massing all of those substances. So we start with the mass of beaker 2, the foil, and the solid. So you can see the solid in beaker 2 to the right. It's a crystalline solid. The tinfoil is not pictured there, but it was included in the mass of 65.979 grams. So on page 39 of your lab manual, in the after separation section is where you'll include that data. Next it says mass of solid. So to calculate the mass of the solid, you need to know the mass of beaker 2 and the mass of the foil. Luckily, we did those masses in the before separation section, so that's where I'm getting those values from. The mass of beaker 2 we weighed when it was clean, dry, and empty, and that mass is shown here, 64.581 grams. We also massed the aluminum foil before we covered that beaker and boiled off the water, and that mass was 0.456 grams. So why do we need to know these masses? Well, if you look, the initial mass, the 65.979, that's the mass of the beaker, the foil, and the solid. And notice we want just the solid by itself. So in order to get the solid by itself, we are going to have to subtract the mass of beaker 2 and the mass of the aluminum foil. By doing that, we are taking out beaker 2 and we are taking out the foil portions and we'll be left with just the solid. So add the mass of beaker 2 and the mass of the foil together. That total is going to be subtracted from the 65.979 to get the mass of the solid that you want. Now, to figure out the identity of the solid, we use our knowledge from the previous video and use the solubilities to figure out what solid is present in beaker 2. So remember, beaker 2 was the solid that we collected was from the initial gravity filtration. So if you can figure out which of the three components, silicon dioxide, sodium chloride, or calcium carbonate, is soluble in water, that will tell you which one, what's the identity of this solid. Because it was for that initial filtration when all we did was mix with water and filtrate. To figure out the percent of this solid in the unknown sample, we need more information. So we can't fill out this portion yet. So we'll put that on hold until after we do further calculations. Next, we're going to get the mass of the watch glass with the filter paper and solid. I have the picture of the solid to the left. It's a fine powdery substance. Now the filter paper is not pictured, but it was included in the mass of 40.394 grams. Now we need to figure out the mass of the solid once again. To do that, we need to take out the mass of the watch glass and the filter paper so that we're left with just the solid by itself. So it's very similar to the last calculation. We're going to take the before separation masses that we collected for the watch glass and filter paper. So if we add the watch glass and the filter paper together, whatever we get for that total, we can subtract from 40.394 grams. And what's left will be the solid by itself, and we will put that value here. Please make sure that you are putting units. So the mass of the solid, all mass is measured in grams in this course, so you would need to put a G after it. Also, take into account your significant figures. Right now what we're doing is subtracting, so you need to pay attention to the decimal places. So what that means is, notice all of my masses have 3 decimal places, so that means my answer should also have 3 decimal places. To figure out the identity of the solid, once again we need to look back to the procedure that we completed. So this solid that was collected on the filter paper. So remember what we did to that solid. We first mixed it in water, so that means this solid that we collected on the filter paper is insoluble in water. We then added 3 molar hydrochloric acid to the filter paper, and what that did is it dissolved one of the substances but left behind this substance. So this substance is insoluble in both water and also insoluble in the HCl, because after we added HCl to it, it still remained on the filter paper. So whatever solid, whatever component is insoluble in both water and HCl, that's the identity of this one. Once again, to figure out the percent of this solid, we need further calculations. So we will save this particular calculation for towards the end. Right, next we are moving to page 40, I believe. Yes. So the mass of beaker 1 and the dried solid, and I don't have a picture of this one. I got 65.035 grams. So we need to calculate the mass of the solid. We want the dried solid by itself. So in order to do that, we need to subtract out beaker 1. So we have the mass of beaker 1 when it was clean, dry, empty that we massed before the separation process. And now all we need to do is subtract these two numbers to get the solid by itself. Once again, 3 decimal places since we're subtracting, use the correct sig figs, and label it as grams. The identity of this solid gets to be a little bit trickier. So we'll look at how to figure that out on the next slide. You would think it's the only component by default that we haven't already labeled, but it's more complicated than that. In order to figure it out, we need to know this equation here. So the solid that is in beaker 1, that's the solid that was soluble in HCl, but insoluble in water. However, the calcium carbonate that was in the original mixture, once we added the HCl to it, a reaction happened and it's no longer calcium carbonate. So you don't want to be writing calcium carbonate here in this blank, because once the HCl was added to it, it actually changed. So one of these 3 products will be the correct answer for the identity of this solid. Now, carbon dioxide is a gas, so that wouldn't work for identity of solid. Water, which we evaporated off in the oven, is a liquid, also not a solid. So by default, you can figure out which of the products is the identity of this solid. Next, we move on to calculations. So in the next slot, it asks for number of moles of this solid recovered. So remember, we just said that calcium chloride was the solid that was recovered because of the reaction that occurred when we added the 3 molar HCl. So to figure out the number of moles, we're going to use the following equation, where moles is equal to mass divided by molar mass. Well, for the mass portion, that's the grams of dry solid that we calculated by subtracting the mass of beaker 1 in dried solid minus the mass of beaker 1. For the molar mass, we need to calculate the molar mass. So they're talking about the total molar mass of calcium chloride, the solid that was recovered. So in order to calculate molar mass, for each element present in this chemical formula, we're going to write the number of atoms and multiply that by the atomic mass on the periodic table. So for calcium, how do we figure out the number of atoms? Well, you can see in the calculation here, I said there's one atom. How did I know that? I look at the chemical formula. Notice calcium doesn't have a subscript after it. If there's no subscript present, that means it's a subscript of just 1. So that means there's just one calcium atom present in this chemical formula. So that gives me number of atoms. But next, I need to multiply that number by the atomic mass. You can see the atomic mass of calcium is 40.078 grams per mole. I got that number by looking at the periodic table, and you have one in your lab manual, I believe on page 81 in the appendix there. So I found calcium on the periodic table, found the atomic mass right below the symbol, and it gave me 40.078. The units are grams per mole. So multiplying across, 1 times 40.078 gives me 40.078. But I also need to do that same process for chlorine, because chlorine is also present in that chemical formula. So for chlorine, notice now for number of atoms I put 2. That's because chlorine has a subscript of 2 after it. That subscript is saying there are 2 chlorine atoms present in this molecule. I then take that number of atoms and multiply it by the atomic mass. So I find chlorine on the periodic table. Gives me an atomic mass of 35.453. Multiply across to get 70.906 grams per mole. To get the total mass of the compound, the total molar mass of that compound as a whole, I then need to add these two numbers together. So 40.078 plus 70.906. So whatever you get for that, that's going to be your molar mass. Okay, that's not the moles though, so that's not the answer that goes here. This is just the molar mass that you're going to use in the equation to calculate moles. So you'll take the mass of your dried solid from your data sheet divided by this molar mass that we just calculated to get the number of moles. And it's going to be a very small number, probably 0.00 something. The units on it is just going to be moles, M-O-L. Next, it asks to calculate the moles of calcium carbonate in the sample. So to do this, we need to know that chemical reaction. So once again, here's the chemical reaction. When calcium carbonate, HCl, was added to it, it formed calcium chloride, carbon dioxide, and water. So how do we figure out the moles of calcium carbonate? Well, we know the moles of calcium chloride. That's what we calculated on the previous slide. So to figure out the moles of calcium carbonate, we look at the ratio of the two. So what I mean by that is we're looking at the coefficients in front of calcium chloride and the coefficient in front of calcium carbonate. The coefficient being the number in front of the chemical formula. So calcium chloride over on the product side doesn't have a number in front of it, so that means it's just a coefficient of 1 in front. For calcium carbonate on the reactant side, it also has no coefficient in front of it, so that means there's just 1 calcium carbonate. So what this tells me is they're equal to each other. It's a 1-to-1 ratio. So what that means is 1 mole of calcium carbonate is going to equal to or make 1 mole of calcium chloride. So if I know the number of moles of calcium chloride, which I do, we just figured that out, that's going to be the same as the moles of calcium carbonate. For instance, say I calculated on the previous slide when I was calculating the number of moles of the solid recovered, remember the solid recovered was calcium chloride. So if I did that calculation and let's say I got 0.002 moles. Well, that means that I would have 0.02 moles of calcium carbonate as well, because they are present in a 1-to-1 ratio. So whatever moles you calculated for calcium chloride, it's going to be the same number that goes here in this blank. Now let's look at a calculation going from moles to grams. So the next blank asks you to calculate the grams of calcium carbonate in the unknown sample. So to do this, we're going to use the following equation, where we take the moles that we just figured out using that 1-to-1 ratio and multiply it by the molar mass. So the moles that we're using are the moles of calcium carbonate. And since the moles of calcium carbonate are the same as the moles of calcium chloride, it really doesn't matter which one you use. For the molar mass, once again, that's something we're going to have to calculate using this chemical formula here. So when we use that chemical formula, what we're going to do is we're going to take the number of atoms times the atomic mass of each. So this time we have 3 atoms present. We have calcium, we have carbon, and we have oxygen. So in the list, I wrote a list of calcium, carbon, and oxygen. Next, you need to write the number of atoms of each. So there's just 1 calcium atom because there is no subscript, so we assume it's just 1. I multiplied that by the atomic mass from the periodic table. So I did the first one for you. So what you're going to do is complete this. Once you write the atoms of each and find the corresponding atomic mass, make sure to add all 3 of those together. So carbon also doesn't have a subscript, so there's just 1 carbon atom. Then you would find its atomic mass from the periodic table, multiply across. Oxygen, same thing, using the subscript, in this case 3, tells you the number of atoms. Find its atomic mass from the periodic table, multiply out, and then add all 3 together. Now that value, whatever you get for the total molar mass, goes into the equation for you to figure out the grams. Now let's go back and look at the percent calculations. So these are the calculations that we skipped for the other 2 parts because we didn't have enough information yet. So what we've done from the previous slide was we've calculated the grams of the last component. Remember, there's 3 components. We have sodium chloride, we have silicon dioxide, and calcium carbonate. So we figured out now the mass of all 3 of those. So in order to figure out the percent recovered of each solid, we need to know the total mass recovered. So using this equation, for the mass of the solid, you're going to plug in whatever the mass of that component is that you're trying to calculate. The total mass recovered is going to be the same in each of these calculations. So for the total mass recovered, you're going to go back to page 39. You're going to find the mass of the solid that was in beaker 2 and add that to the mass of the solid that was on the watch glass. And then add that to the mass of calcium carbonate that we calculated on the previous slide. This will give you your total mass recovered that will go in the denominator of this equation. Make sure you are going to be using this equation 3 separate times to calculate the percent solid for all 3 components. So one time you'll take the mass of the sodium chloride and plug that in for the numerator and solve. Second time you will take the mass of the silicon dioxide and plug in for the numerator and solve. And then last but not least, the calcium carbonate. So you get 3 different percents. This is important because if you look back on page 40, it asks you for the percent recovery, which is the sum of the experimental percents. So we need to take those percents that we just calculated, the percent of sodium chloride, percent of silicon dioxide, and percent of calcium carbonate, and add them together to get the percent recovery. We need this to do the last calculation, which is percent error. So looking at percent error, the equation is experimental minus theoretical and then divided by theoretical. Notice there are absolute value bars. This means that you are going to get a positive number. So even if it shows up negative in your calculator, just change that negative to a positive. So what are you using for your experimental? That's the percent recovery that you calculated when you added the percents of each component together. When you added those percents, you should have gotten somewhere around 100%. It's not going to be exactly 100. It was either going to be a little less or a little more. Now for the theoretical, you're going to use 100% because what theoretical means is how much should you have gotten if you did everything perfectly and lost no material anywhere. So you should have gotten 100% if there were no mistakes, but there is human error, so you're not going to collect all the material. So that is it for the calculation portions. Now notice there are a few theoretical concept questions after this calculation. The first one being talking about the compound dried in beaker 1 has a tendency to form a hydrate at room temperature. So we're talking about the calcium chloride. So what a hydrate is it's an ionic compound that has water molecules trapped in its structure. So the hydrate, since it has water molecules trapped in its atomic structure, it's adding mass to the compound itself, to the beaker. So that should help you answer the rest of that question. And the next one, why were the filter paper and solid allowed to air dry and not heated in the drying oven? So think of what might have happened to the paper if it was in the oven for a long period of time. That should help you answer that one as well.